Hi everyone, welcome back. We're going to continue our discussion on electrical potential. Okay, so this is the start of finding the electric potential of a point charge. Okay, so previously we were looking at a uniform electric field, but now we're going to look at a point charge. Okay, so this is what has been calculated and found, that the electric potential is equal to K, which is a constant, times Q divided by R. Okay, so we're going to use that equation in order to solve this first example here. Okay, so again, when I say a point charge, I mean literally just a little charge. Okay, so whatever the electric field that's produced, and then whatever that potential is around that, okay? And we'll look at this graphically in a bit, okay? So this first example states, what is the voltage 5.0 centimeters away from the center of a 1 centimeter diameter metal sphere that has a negative 3.0 nanocoulomb static charge. Okay, so this is our charge, Q. This is our distance, R. Okay, so we want to find our voltage. V is equal to K times our Q over R. So let me find K, since it is a constant, real quick. Okay, so this is the K that we looked at last chapter, but I don't remember off the top of my head. So it's 8.99 times 10 to the 9th. Is it Newton meter squared over Coulomb squared? Newton meters squared over Coulomb squared. Okay, so this is that constant. All right, so then we can just plug in. We are treating this metal sphere with this very small diameter as a point charge. Okay. All right, so we have V is equal to our K, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, times negative 3.00, and I'm going to go ahead and convert our nanocoulombs. So NC is equal to 10 to the negative 9th C. Okay, so I'll say times 10 to the negative 9th coulombs. And that's going to be divided by our radius, which is 0.050 meters. Okay, so we can plug this in. Whoops, 8.99 times 10 to the 9th times 3 times 10 to the negative 9th. And we divide that by 0.05, and we get, remember that it's negative, 539. And this is our voltage. This is going to be in volts. Okay, so this is our voltage of, the metal sphere. Okay. Okay, and note that I will tell you that it is a point charge when I want you guys to calculate it, or it'll be very obvious, okay? All right, let's look at a new concept called equipotential lines. And this is a way for us to represent electric potentials. Okay, so we are looking at, in this diagram here, a charge Q, okay, with an electric field. We have electric field lines here, okay, and then you start seeing the equipotential lines, and that's these circles here, okay. So let me list out some properties of these. So the potential is the same along each equipotential line, okay. So if this line here, this entire circle, if I want to take the potential, it's going to be the same at every single point, okay? That means the potential difference is 0 along those lines, okay? The potential is not 0, but the potential difference is 0, okay? Speaking of that, there is no work required to move along those lines. So if I have an electron and it's just moving along this line, it doesn't do any work, okay? Because there's no difference in the potential, so there's no potential difference, and therefore we don't have a change in potential energy. Therefore, no work is done, okay? But if we were to move from, say, this equipotential line to this one, so this one to this one, there will be some work that needs to be done. You have to have some sort of work to move from one equipotential line to another, okay? One other property is that they are perpendicular to electric field lines. So as you can see, we have our electric field lines here, okay? If I were to say extend, maybe I'll extend this guy here, whoops, okay? At that exact point, it is going to be perpendicular, okay? So at this exact point, okay? And that's going to be true for all of these. So at each point, we have a right angle here that it's making with the equipotential line and the field line. Okay? All right. This is a concept that maybe you guys already know about, but it's called grounding. And it's useful for safety. You can ground yourself to a metal ground a metal object, a metal case of an electrical appliance, ensures that it is 0 volts relative to the earth. Okay, this sounds very obscure, but let me give you an example. A major thing is when you're driving a car and you want to go get gas, and maybe you've been taught this, maybe you haven't, but there can be static electricity, that builds up on you as you drive. And if you go to pump your gas, you need to discharge yourself. So you need to touch another object or surface that is metal in order to ground yourself. Okay. So one thing that I usually do is touch the inside of my door, or most of my car is metal. It's an older car, so I can pretty much touch just, the door handle or whatever that's metal to do that. Okay. That'll disperse any static electricity or static charge that's built up on you. Okay. This is important because any kind of spark between you and the gas could cause it can cause an explosion. So you don't want to, I wouldn't say, maybe it's not that bad, but this is what I grew up understanding. So just be safe, discharge yourself, or ground yourself before you pump your gas. This is also why you shouldn't have your phone on you. A lot of us have cell phones. You should leave that in the car as well when you're pumping gas. Okay, that's just a quick PSA with static charge and electric charge. Okay. All right. So I am going to quickly show you guys multiple charge electric field and equipotential lines. Okay, so this is where we have a positive and a negative, so attraction between two charges. Okay, so we first draw our electric field lines, right? So it goes from the positive to the negative. That's why we've got these arrows here. Okay, so we draw those. Then we can start drawing our equipotential lines based off that. Okay, so what I would do is I would start going along with our lines here, and then just start drawing perpendicular lines. So here, 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 and so forth. Forgot that one in the middle. So I just start drawing some of those, and they are spaced a certain way. Okay, so equipotential lines are measured with a voltmeter in labs experiments. Okay, so I'm not just going to randomly draw those, but I'm going to be meticulous and say, okay, along this line I have this many volts. Say I have 1 volt. Okay, and the next one is 2 volts. Okay, so this is how it goes, and you would go around and check where that next 1 volt is, where it crosses on, say, this electric field line here, and so forth. And so this is how you eventually get that pattern of the circles. They look like circles, okay, or some kind of ellipses, okay. So this is the idea, and I hope that we can do this in lab. If not, maybe some sort of online supplement. I'm not positive yet, but I think this would be really cool to do and actually map out on paper so you can see this in action. Okay, it's not just something that physicists kind of came up with. It is something very measurable. We can measure this in lab. Okay. Oops. Okay, and then let me uh, erase the ink. Okay, so this is another example. This is with two. Sorry, these are with two charges that are the same. So these are the same signs. We have a negative and a negative here. Okay, and we do the exact same thing. So remember that opposite charges attract, but same charges will repel. So in this case, we have our electric field lines, and they are not going to cross, okay? And this is what they'll look like when we have two negatives. And then again, we can start drawing our equipotential lines or taking measurements in lab, okay? So again, these are really small to do, but we'll see them here, okay? And then because we don't have anything crossing here, we kind of just leave it blank in here, okay? And we connect it like so, okay? And again, this is when we have same charges or like charges, okay? Here is an example of the voltages that you'll see when we take a voltmeter and we measure the voltages or the potential differences, okay? So we've got negative 10 volts here, then it goes to negative 5, and then negative 2 all the way out there, okay? And you can even follow this curve. This is kind of, a guess when we just start drawing it, but once we get our voltmeter out, we can measure that and follow these lines. We can follow these equipotential lines by taking a measurement, say here, and then here, and then here, and so forth. Right? All right. I'm going to pause. There's another one. Oh, I forgot how many I added. Okay, so here is another example of equipotential lines, and this is between two parallel plates. Okay, so we have positive charges on this plate, negative charges on this plate, and you can see the electric field lines. Right, these are our E field. And then our equipotential lines look like so. Again, you can see it pretty clearly here that they will be perpendicular to each other. Okay, so you can see that pretty clear here. And again, you can follow this and it'll show with a voltmeter that this is all 75 volts and this is 50 volts and so forth. Okay. All right, I believe that's the last one now. Okay, so I'm going to pause here and then we'll start the next section talking about capacitors and capacitance.